Good morning students, this is Usha from G.K.Jain High Secondary School. Today we are going to see the chapter Properties of Matter in 11th Standard Physics. In this we are going to learn about the Hooke's law. So in my before video I have given the explanation about the stress and strain. The formula to find out the stress is force by area and for the strain is change in length by original length. So now we will move on to the Hooke's law topic. So now we will take a stand and we take a spring which is attached to a pointer. Now the spring, one end of the spring is attached to the support and the other end of the spring is attached to the pointer. That is the other end of the pointer. The other end of the spring is attached to the pan. Now we are going to add weight to this pan. So what happened? The spring elongated. So as spring elongated, the length increases. What happened to the area? The area decreases. This can be proved by small demonstration method. I'll prove you now. This apparatus is nothing but you will do it in your lab, spring constant. The same experiment I'll explain you. This is a stand we are going to take and I am going to attach a spring to it. Now a weight hanger is added over here. To identify the values, it is being given in the green color. The pointer is given in the green color. Now you can see here, now I am going to add a weight to this. When I add a weight to this, the length increases in the spring. Now the pointer shown over here is 20, right? So now I am going to add one more weight. Now the pointer shows around 24. So which proves that as I add over weight, so the spring expands, right? From this we can say that the stress is directly proportional to the strain. The stress is we are adding the load. Accordingly, the strain is the length change. So this is the experimental verification of your Hooke's law. By using this value, a graph is drawn by taking your force along your x-axis and your extension along your y-axis. Now this is the slope. Let we draw two perpendicular lines from here as well as along your y-axis. So let F be the smaller portion that we consider. Here delta L be the portion. Then slope is equal to delta L divided by F. Now what I will do, I will take this force to the other side. So what happened to my equation? So my slope into my F value is equal to delta L. We all have learned that volume is equal to, what is the formula for the volume? Volume is equal to area into the height. Here the height is L. So I will write it as A into L. Now in this equation, above equation, I will multiply and divide by AL. So what happened to my equation now? Slope into F is equal to delta L AL divided by AL. Okay. Now what we will do? This slope I will take it down and 1A I will bring it here. So the equation becomes F by A is equal to this A I have brought it to the other side. So what now the here equation becomes, right, here A I have taken, so I will get it as L divided by this A into slope I will write. What is the remaining term I have? Delta L divided by L, right? So this is my answer. F by A is equal to L by A into slope into delta L divided by L. As I said you, force by area is stress, which is given by the symbol sigma is equal to, right, change in length by original length will give me strain, that I will write it as epsilon. So now according to my Hooke's law, within the elastic limit, the stress is equal to the strain produced. So this is the experimental proof. Now we are going to see the stress versus the strain profile. In this we are going to take the strain along your x-axis and the stress along your y-axis. We have marked the different points here. Let me name it as O, A, B, C, D and E. According to the point O be the origin. Now we will consider here the line OA. Right? Here the A point is called as limit of proportionality. So the stress is directly proportional to the strain. That's why we got your straight line here. As the stress is given to the object, when you remove the hand or remove your work, so what happens once again, they come back to their original position, right? So they are going to be equal. So when you leave your rubber band, example we can take the rubber band, right? When you stretch your rubber band, so the rubber band get expanded. So the strain produced due to the force you have applied. Once we leave our hand, what happened? Once again it regain its original position. So this is a line OA, which is called as your limit of proportionality. Here Hooke's law is valid. Let me take the other point, the B, which is called as your yield point. That is, this is the point up to the elastic limit. This also we can say that the stress is proportional to the strain. So when we take the same rubber band, expand over it, and when we leave your hand, so once again it come back to the original position, but little bit the shape is changed. So that is called as your point B, right? Elastic limit point, right? So here the Hooke's law is invalid. Now we will move on to the point C. So which we say that the same rubber band, when I expand, right? When I leave my hand, the rubber band takes a new position, right? They won't obey the Hooke's law, right? Hooke's law is invalid at the point C. So it went beyond your elastic limit value. Now we will consider the point D and E, right? So D point is called as ultimate stress point. So where the maximum stress can be given, so that point is called as your fracture point, where they won't regain their original shape at all. They are moved above the elastic limit and they may move out of the track. So this point E is called as your breaking, or it is called as rupture point, right? So this is the graph which is shown here, right? The relation between the strain and stress up to the point O to B, it is in the limit, elastic limit value, where the stress is directly proportional to the strain, and Hooke's law is valid. Above the point B, Hooke's law is invalid. That is, above the point A itself, Hooke's law is invalid. And when we move to the point D and all, the ultimate stress point they attain and they will break up. So this is the graph which proves your stress-strain relationship. Now we move on to the next topic, moduli of elasticity. There are three types of moduli of elasticity: Young's modulus, bulk modulus and rigidity modulus. First we are going to see the Young's modulus. So when we talk about the Young's modulus, so whatever the stress given to the object, the strain produced, we are going to calculate. So the formula for the Young's modulus of the material is given as tensile stress or compressive stress divided by tensile strain or compressive strain. So this can be written as Y is the Young's modulus of the material, the symbol we use here. So Y is equal to sigma T divided by epsilon T or sigma C divided by epsilon C, where sigma T and sigma C are tensile stress and compressive stress, whereas epsilon T and epsilon C are tensile strain or compressive strain. As we all know that the stress unit is given as Newton per meter square, and for strain no unit. So the SI unit of Young's modulus is given as Newton per meter square. Now we are going to see the bulk modulus. Bulk modulus is represented by the symbol K, which is normal stress or the pressure to the volume strain. First we will calculate what is your normal stress, that is the pressure. So which is sigma n is equal to Fn divided by delta A. As we all know, the stress is equal to force by area, and your epsilon s is change in volume by original volume, delta V divided by V. Substituting these two values here, so we will get K is equal to delta P divided by delta V divided by V. So this is the formula used to find out the bulk modulus of the given material. So compressibility C is equal to 1 by K. Reciprocal of bulk modulus is called as your compressibility. The next one is going to be rigidity modulus. In this we are going to see the symbol eta R, which is given for rigidity modulus, which is nothing but shearing stress by shearing strain. So for this we can do it by a small experimental, that is, you are placing a sponge on the table, you are fixing one side of the sponge on the table. Now when you apply a force over here, so what happened, the sponge will move to a certain, that is on the upper layer alone it get turned. So let it angle made by them be theta. Let h be the height of the sponge and x be the distance that being moved. Then I am able to find out what is the shearing stress and what is the shearing strain. So sigma s is equal to Ft divided by delta A, and your epsilon s is equal to h by your h value, which can be taken as theta. So when we substitute these two values in the given equation, I will get eta r is equal to Ft divided by delta A divided by x divided by h. So this can be written as Ft divided by delta A divided by theta. By knowing this value, we are able to find out the rigid modulus of the given material. As the value is going to be increased, the twist is going to be very less. Thank you, students. Now in this class, you have learned about the Hooke's law and the experimental verification, and you have learned about the graph, how to draw the stress strain graph and the explanation, and 3 moduli of elasticity. Thank you. Once again, we will meet you in the next video.